Okay, so what you do with all these big data sets, right, is you take off a little piece that you can put on your laptop or your iPhone or whatever, and you mess around with it. Like you have something like maybe you want to create networks based on how people reply to each other. So you do a little bit of that. You test it out, and if it doesn't explode on your laptop, then you go to the, for us, we go to the VAC. And then you make the VAC explode a few times, right? So you know, you guys, anyone use this at all? The Vermont Advanced Computing Core was the center. Shut up. So he destroys it regularly. So how big is it now? It's like 1,500 cores or something, or is it much more? It's a lot of machines. It's a lot of machines. And that's where the data is, right? So you get in there and you just start opening up things. A lot of stuff's zipped up, but now we have a way of, you know, getting at things that are zipped up, of course. So yeah, if you want to do the whole thing, that's a lot. But so the geodata, as I said, is smaller. And it's actually really in one database. Yeah, so you can really get at that. So 1% of people tweeting, or things, entities, bots, include geodata. Yeah. So that includes really, you know, weather stations, ambulances, right? So there's a lot of stuff to filter out there. Yeah, it's like so if you do this kind of mindlessly, you're getting a lot of trouble. In fact, there's a piece of.
Can you like see if like an individual is on it? Is in your
Sure.
data set?
Mm-hmm. Oh, absolutely. No, there's a real problem. I mean, well, it's not a real problem. It is an open data set. It's not like we're looking at. It's not like we're NSAing the thing with email that we somehow sneakily got. It's open data. So yes, everything we do is not a. It's all population level. We wouldn't put in. We would never publish, like here's a publication and here's a representative tweet, because it's just wrong to do that, because it's not representative. You already, you've curated it in some way, and plus you get into lots of trouble. Look, well, there are viewers. You made one, but there are viewers of tweets going on now, so you can look at UVM if you want. You can just zoom in and you'll see like, oh, here are little tweets, and people, I mean, it's just open stuff. We had it up once in our group meeting, and there was a nice. We zoomed in on one, and it was I'm going to make this chemistry exam my, like, good kid, good student. It's like, yes. It's like psyching up. Like, who's a good, like, they're in their room saying. Yeah, well, they're psyching themselves up. I totally approve of that. There are other things they say that aren't quite as impressive. Okay, Twitter plotter. Twitter plotter? Do I can I just get it with this?
Go to my website, cvm.edu/Twitter. No, not that whole thing.
That's what it wants to do, so I'm going to, yeah?
Yeah, Twitter plotter with a capital P.
Yeah, you would do that.
As you should. Underscore. No,
So I'm trying to get it to fit here. Okay. Chicken.
you need to trust the plot.
There you go.
Yeah, mine's South Africa.
All right, Australia. Let's see what they're doing here. This is where it all goes wrong.
Reading the tweets.
Yeah. Yes, we never do this. This is very dangerous. I don't know. Obama. This should be a good.
So no, show them the scary part.
Oh dear. Yeah, it's gone wrong. Goes wrong so quickly. Sorry, people. Okay, we'll edit that out. Anyway, they're tweeting the truth, apparently, of what they think in their heads. Okay.
And you can zoom in and find out where this person is.
Yeah, so.
Like very specifically.
Like if they're in Disneyland, what do people tweet if they're in Disneyland? I mean, there's just, you have to ask good questions eventually, but this is just to give you a sense of how big things are. All right. Anyway, this is for you guys who've just come, right? So the 10% of all tweets, we have it. Lots of different questions. You can come up with questions. Fun thing to work on. And the data's in, somewhat manageable form, especially so the geo stuff is.
Is it anonymized?
No, absolutely not.
So you know the full user
You have a full thing. So each tweet is a JSON. Each tweet is a piece of JSON, which, if you put on a normal kind of screen, is really fills up the thing, right? So it's just full of stuff. There are, a retweet will have the original tweet inside it. It's very biological after a while. Like it never used to be like that. They just sort of point to the tweet, but they actually carry it inside it. So all the data about it, right? All the metadata about that tweet. And this is a retweet. You see, we get deleted tweets. So if someone deletes a tweet, we get that it was deleted. And again, 10%. So that's a whole thing to study. What's the texture of deleted tweets versus ones that aren't deleted? So there'll be spelling mistake ones, but then there'll be, some interesting ones. I don't know. We've done a lot of stuff. I will talk about it again later in the semester, but we've done a lot of stuff looking at, what's the texture of the US in terms of just word usage, things like emotional levels, how does that correlate with everything you can imagine that we measure in other ways, obesity levels, whatever it is, right? Poverty, all sorts of things. And it's pretty strong. Okay, so everyone, of course, wants Twitter to predict when the next, social disaster happens or something, or how to make money. I don't know about that. So we were talking about this before. I'm just going to show this. This is kind of an excellent little study. It came out of New Zealand. Here's a write-up about it. So they went through all the minifigures, 6,000 minifigures from 1975 onwards. And they did this. These expressions are kind of, these are the ones we can express with our face. This is sort of right. So there are 4 negative ones: angry, disgusted, sad, and fearful. Surprised is sort of neutral, and you can add them with the others. And then happy, right? And you can dial those expressions up and down, and then you can combine them, right? So pity is some mixture of sad and happy, actually, for example. And horror would be, fear and surprise, probably, and disgust, and sad, right? It's a mixture of all sorts of things. Okay, so they use a very standard thing, and they got people to rate them on Mechanical Turk. So the paper is here. It's kind of great. They have figure 1, a Lego minifigure. It's pretty good, but they're big, and here's a taxonomy of them. This is a taxonomy. It's kind of great. There's Spider-Man. This is a Chamber of Secrets, so this is all the Harry Potter stuff. Is this space? Yeah, this is just space. Right, it's kind of great. It's an interesting piece of knowledge you have in your head, which you may have. You done this?
Yeah.
Okay. You really can do that?
No, my best friends, when they got married, their cake chocolate.
That's pretty great. Yeah. So these are the official ones. These are the official ones, which apparently one of these guys must have had in their basement. Yeah. They took pictures of them all. Anatomy. They're killing it. So they. Thank you for that. That's figure 3. So we've had taxonomy. So there's a lot of just like, let's just get into this and understand the, the story here. And then this is what you're given. You've got a picture of one guy. So they took pictures of them all. I mean, I think they took their own pictures. They're not sort of scraped off the Lego website. And then you have to rate all of them. Anger, right? It's a 5-point scale, right? Least to most. And then their results. They have this kind of thing. So there's stuff like this. Number of new heads. And where do they have this? Okay, here are some examples. So this is sort of the main one, right? These are some examples. So there's disdain. These are more complicated faces as well. So fear, happiness, anger, concern, evil concern, and confidence. So this is, there weren't many to start with, right? So that's this is pretty bad, actually. But then their big story was this is anger. And there's a little bit of fear and surprise and so on. So there's been this basically expansion of emotional states being represented. Of course, they have I think for the 2-head thing, because you can flip them around and change the hair, right? There's a face on either side.
Yeah.
For some of them, right? So they did that, and I think they randomly chose one side. It is pretty awesome. There's no doubt about this. New Zealand. This is New Zealand, people. This is where it's all happening. There's a guy from Poland as well, or a woman, I think. And then we have, I don't know. But yeah, these two are at Canterbury. So while they were not thinking about rugby, which is pretty much what New Zealanders do, they were doing this. Yeah. They don't think about cricket because that doesn't work out. Skin colors, they talked about skin color. Yeah, like, does that affect it? Anyway, look at this. I mean, they've got, 50 citations. Great. Really solid work. But that was their big piece. Anyway, yeah. Yep. Really good. Okay. Well done, people. So I wanted to add a few. So we're going to talk about small world networks again, and then maybe get into scale-free networks. I wanted to add a little bit to what we had the other day. So we looked up the papers here, right? I looked on the Wikipedia page. So Natalie Portman's birth name was Hirschlag. So that's what's sitting. She was born in Jerusalem, and she has a. So yeah. So she kind of, yeah. As many of these people do, change their name. So Hirschlag is not the name she carried into all of her films.
So how is she related to Erdos? Just because she is a paper.
Okay, so this is what we talked about this the other day. So Natalie Portman's got 5 or 6 papers or something like that. With she was at Harvard, yeah, and she's been in the movies a little bit. Yeah, no, right. It's like a bio thing. Yeah. Anyway, so we couldn't find her name, but it's because it was N. Hirschlag, which she just used as a.
Is her professional name or this her?
Just, I don't know. It probably didn't want to. I don't know.
It's her maternal grandmother or something.
Okay, so it's a stage one. Is that? I might have this in 2 places because I've done the wrong thing. Oh yeah, I added this. I wanted to mention this the other day. So Dan Kleitman, so he's one of the 3 big heroes of combinatorics at MIT, developing it many years ago. And he has a Erich-Bacon number of 3, so 1 plus 2. And so there's some disputation about whether he should get one for being in the movies. But he was in this movie, Good Will Hunting, a couple of times as an extra. He's walking around in the background and so on. So, do extras count, obviously. So obviously a thing you could argue about a lot. If you want, later on, you can look at this great little review of the movie, which is just a serious review of the movie from a mathematician's point of view. And he has a little piece in there that talks about the whole thing. So one day at the applied math, so this would have been, I'm pretty sure this is all right. So it must have been 95. I walked into the applied math common room, and there are 4 guys in suits sitting down and talking to Kleitman, who's kind of crazy, right? So he's like, wow, he's sort of famous for, we run this seminar where there'd be a pile of papers, and he'd just pick one off the top and say, oh, this is wrong, and then just proceed. That's kind of how he did it, like fix it up, instantly. Brilliant guy, but sort of a classic kind of crazy professor sort of thing. So they were asking him, like, can you just put some things on the board and stuff like that, They're all surprisingly good looking, which doesn't really happen. Like the math department, it was very dressed well, and so I'm sure in a few years later, I'm like, oh, it was Ben Affleck, right? I mean, that was that's what I was setting it up, because he did make, combinatorics is sort of a thing that's plausible that someone could figure out if they're from South Boston and don't have an education. So that was the setup, right? He's this genius, So it was so he drew a few things. Anyway, that's where it comes from. Had a few tweets back and forth with Strogatz, who wants his number to be the lowest one. We talked about that, right? Because one of them was a documentary. Anyway, he was questioning the validity of this claim that's a 2.
Is Strogatz a 2?
He's a 3 because he's been in a document. Oh no. So he's a 2 with Edish. He's a 2 with Edish. He's not connected to Edish directly, right? Yeah. But he's got a 1 because he was in a movie about the small world phenomenon, which was a documentary which had all these scientists, like Watts and so on, and Kevin Bacon. And I guess Kevin Bacon eventually adopted this. It's a parlor game, but he's like, okay, that's sort of good, and then try to make a good thing out of it. So this may be in some different places. Okay, so I wanted to.
These mathematicians want to meet him just so that they can lower him.
I think real mathematicians were really keen on the Edish connection, but but they should, yeah.
Sadly true.
I mean, that one's hard to
Not
make
in
now, because
India.
you can't meet him, so you can't drop that number down too much.
Which one? The
The
Edish, yeah, you're in trouble there.
There's lots of 2s, and there's a few.
Could be an unpublished manuscript that you just found. You could always go that route. Yeah.
There's the XKCD, right? Where
Is that what they're doing?
it's the apocalypse, and all the math grad students are like, hey, it's the apocalypse. Like, everybody get together and like, fly over to Erdish's grave. We get you to sign.
Co-author.
Yeah.
Nice touch. All right. All right, so it's fun. Not necessarily meaningful, but if you have, and the thing about the acting, of course, is it's very thin. You just have to be in the same film, credited as an actor. So yeah, the thing was, Kleinberg did these things, and then they said, "Would you like to be an extra?" And he thought it was great. So I think there's some scene where he kind of walks past at Harvard Square in the background, and then if you watch it, he walks past the other way a bit later on, and it's sort of not the best. Anyway, so we finished with this. We're talking about the red balloons thing. I think we talked about much of this, and it was the whole small world search thing, right? So how do you navigate around networks? And so this, if you like, experimental kind of algorithmic work that they came up with was all about making the incentives work, and that was very, very clever, right? So it's not a Ponzi scheme. You can see the interview later on. It's good fun. We had this stuff. And they did it very quickly. It was just a few days. So, it opens up this possibility of what was the title of their paper? They framed it well. Time-critical social mobilization, right? Obviously, this could be used for good things and very bad things, So that's what science is about. Producing technology for which you can explode your planet, or make it better. So the game is, all right, what things can we do this for? This was a bit of fun. It was a kind of a nice puzzle that MIT's brand worked. That helped. But what about, I don't know, solving a shutdown or something like that? How do you get people together to? I mean, we have all sorts of crowdsourcing going on all the time, and markets are crowdsourcing things. So. It's been going on forever, right? Language is created out of a crowdsourcing structure. Okay, we kind of forget about that. All right, so this is a great thing. It came along in the last few years. So we're going to go back to, we've had experiment, some sort of practical applications, right, inspired by, and there's still work coming out. There's some work a few years ago by the data team at Facebook showing the average degree is 4 for everyone on Facebook. But it sort of retreated back to just this structural story, like what's the average path length between everyone, shortest path length. There's nothing about searchability, nothing about whether it's useful or not, or do people actually functionally do anything. It was mainly, here is a ginormous network that no one has ever been able to kind of get at, and we did it, right? So that was a computational thing. All right, so let's go back to the theory of these things. You've seen how it's been used practically, but there's a lot to kind of understanding how it might work. So the initial story is this, right? That connected random networks have a short average path length. We've talked about random networks a little bit. You've looked at them in your assignments. You can compute this yourself for some simple things, but the main thing is, and you've seen this now, that locally, I'll be careful with chalk inhalation. Random networks have no clustering, right? They have 0 clustering. So you call them branching networks, right? They're locally branching networks, right? So there's no sociality to these things, which I'll say again. But if you kind of have the average number of friends that someone has and the average number of friends that one of their friends have and so on, we'll come to this later on when we look at contagion, then you fairly quickly scoop up everyone. If you go out, you have, there's some growth rate here. 4 times 4, whatever it is, 10 times 10 times 10. You get to a lot of people pretty quickly, which was the NSA problem, right? 3 degrees of separation kind of covers everyone. And you can see that it grows slowly. Then the average shortest path, this is average shortest path, grows slowly with the number of nodes for these kind of pure random networks. Right, grows as a logarithm. So that's a good first part, right? So you don't want a giant world that's simply hard to navigate because, right, if everyone was on a line and you just had one friend each on that line, and you wanted to send your message to someone who's way down there, the message would have to pass one person to one, right? It just would simply take a long time. I mean, absent any algorithm problems, right? Even if it was purely directed, right? So that's a first piece. And so it was noted that random networks have this property of smallness. Right? So that's the first thing you might think about when you say small world. This is really probably the defining piece to start with. But then these aren't social. This is completely wrong. This is not a social world. It's not an information type world. Information doesn't look like this, the way things are connected. Wikipedia pages don't look like this, right? Knowledge isn't like this. Got a bit of a wheeze here. Right, so social networks aren't random. All right, so small world. So that's the small part of it, but we need social, and then we'll need navigability. Right. This I'm just throwing in. It's probably in the wrong spot. It is on the wrong page. Okay. Yeah, it's supposed to be on another spot. All right, I'll move it. There's a story here about finding a panda that escaped. So, you know, we've used this sort of thing for a long time. Pandas, right? We've lost our panda. I know, sloth capture would be. Right, it's true. That's true. The kung fu thing kind of.
They would probably just like fall over a railing if that's how they would get lost.
They'd start eating something and just sit down, right?
You wouldn't really have to look.
Yeah, that's true. But apparently it did get away. This is just one example of where, you know, many people are looking, right? You have, I mean, you have everything from cute things like the pandas to very bad things like Amber Alerts, right? Where you've got everyone trying to find something at some point, and people are, you know, wanted posters, right? I mean, the very old school. I mean, we were using collaborative, you know, social kind of help, right? You know, you get a reward for turning someone in because of connections and so on. So this should be back, I'm sorry. But this is a story, it was crowdsourcing in manhunts. This is actually about, so I mean, just to show you this keeps going on, I have comments in here. This is Philip Ball. It's the Boston bombing, talking about the Boston bombing. So Reddit, right, there was kind of this, well, it was framed as a witch hunt afterwards by Reddit. You know, they kind of put up pictures of the wrong person and said it's this person, or maybe it's this person. And they did do some things, of course, very well, right? So they were able to find a picture of the person once the suspect was kind of identified. They dug through and found all sorts of things. But it can go wrong, you know, it can go wrong. So, but I think that, and then the general media thought this was hilarious and great, right? Look how terrible social media is. You should just watch us on CNN in the Situation Room or the Fox News, what is it? News Death Star? What is it? Fox News station? No, it's a Fox News.
That thing I saw.
Empire. What is it? It's the Fox.
Newsroom or something.
It's got a.
The large area.
What is it?
Yeah, the big area touchscreens are bad.
So there's that one. I mean, you know, the Situation Room, the ones where you slide things around, all this sort of stuff. Right?
But if you're ever comparing like your productivity to Reddit,
Yeah.
you've got to really.
You're right.
Like that's where productivity goes to die.
Well, I mean, so that, you know, one could argue that next time something like this happens, they'll do a better job, right? They'll learn from this, and they'll be jumping on top of each other saying, no, are you sure? You know, I think that's probably going to be the case. And this is something we talked about years ago. In fact, I wrote proposals about this, what I call the collective detective. And one idea we had of the small world thing was to find people. And I mentioned this the other day. Find, you know, there's some person you haven't seen for years and you want to catch up with them somehow. And you use this kind of small world search thing, right? But of course, it seemed to be like a great thing for stalkers, you know, which Facebook basically is, right? Yeah. Mark Zuckerberg, yeah. At least that's what the movie said, right? So, okay. Anyway, that was supposed to be back. I'll fix it up. Okay, so we went from random to, random has this property of smallness, but it doesn't have socialness. So it's obviously wrong, right? So it's cheating a little bit to kind of be greedily, if you start somewhere, you can get to most people very quickly. Of course, it's manifestly unsearchable because you have no idea where to go, right? There's no map. So this isn't, so if you start to add some clustering in here, does the thing blow up and expand too much? Does it become too big, right? Okay, so say this again. All right, so you've got to this, right? So there's this node and they have, these are their friends here, and then the dashed lines are the connections between their friends, and so there's clustering, right? So this is a natural property to ask of a network, and it's the thing that Watson-Strogatz put together when they were looking at their models. And I should say their work was inspired by crickets, actually, right? So Duncan was, so Strogatz's big thing is synchronization, right? So one of the things they were doing was getting crickets and playing a little electronic chirps and seeing how long it took them to chirp back. Like trying to get your cricket to, you know, synchronize with some electronic thing, and then changing the frequency of this and basically see if you can make the cricket explode. You know, like was there a phase transition where it couldn't do it anymore? Seeing what its little oscillator structure was like by testing it. So, and I think this is true. Duncan was out in trees trying to find crickets, bring them back in jars and put them in a lab. And then they started to think, well, what if we had, you know, what if we could set up tubes and you have your little cricket here, right? And you put some headphones on this guy, and they can only listen to, you know, other crickets that are sitting over here, right? Like, how would that work? Instead of it being in a big, you know, crickets are all like this. They're expanding like the fireflies. They can hear each other locally. Yeah. But what if it was some network structure? There may be a tube system, something like that, and a series of tubes like the internet. Yep. And just like the internet. Yeah. This guy's chirping away. There's maybe a little top hat, something like that. Okay. So what would happen? You know, if you had like a ring, would that work? Yeah. What's that? Would it, you know, how quickly would it work? You know, what do you need to make these crickets synchronize and get their chirping, you know, working, right? Cicadas and so on. I mean, they're all. Do cicadas synchronize? I don't know if they do actually. They just make a horrible noise. There's that bit, yeah, the 17-year thing. But I don't know if they really do make a lot of noise. All right, so anyway, that was kind of, they started to think, well, what about this, right? And then they kind of set the crickets aside because this is going to take a lot of crickets and tiny earmuffs, which were technically hard. Someone should totally do this, by the way. And they probably have. Someone, I'm sure someone has done this. Okay, so that was the inspiration for thinking about networks, right? So like, okay, well, let's put things on networks and then see if they synchronize. What about diseases spreading on them? Good question. So I'll show you the example the model they actually used. There's a number of models, of course, in the great tradition of science that didn't work and weren't so great, and then you get one that does something, and you're like, oh. So what if we have this? This is obviously not very realistic sort of social network, or any kind of network, but A and B are here. And this is kind of the example I was talking about before, right? So if A wants to send a message to B, then they don't understand this grid structure, then they choose one of their friends somehow, and then the thing gets moved and moved and moved. There's some clustering here, like this to all of them. So these ones have zero clustering around them. Oh, sorry, no, they do. They have clustering around them. They have an odd kind of clustering. It's a bit of a funny kind of network. So we've introduced clustering, but this is an example of how now it sort of pushes everything out, and now the distances, the average shortest path is kind of large again, right? So we'll add a few pieces, just add a few links. It turns out that in general it doesn't take too many. And of course we'll be thinking about very large networks and so on. You add a few links, and of course these ones have been chosen ridiculously, especially. So if this person turns out to know someone over here, you know, maybe they used to live together, then bump, 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 and they understand something of this structure, then they'll know to send it here, pick up the phone, send a tweet, whatever it is. So the average, so you just put a few of these, and this is just one pair. Now, of course, average path length is about all of these pairs. So you take every pair, find the shortest path between them, and then average over everything. And so, you know, all of these guys are going to be helped by this shortest path. Everyone here is going to be helped. You know, it'll be better for them to actually walk in towards this. It's like taking a flight, right? They drive into a hub and then boop, go off there. As long as they know what this pattern is like. Fair enough? Okay, so the original title, so the original piece is Collective Dynamics of Small World Networks, with the quotes. And it was, I think it's Joel Cohn at Rockefeller who's did a lot of work on food webs, right? So theoretical ideas of food webs, that sort of thing. Many other things. Who I think one of these guys was presenting something there and about these, and of course they're still thinking about crickets and synchronization. And I believe this is a story. Cohen said, what do you think, you know about Milgram's thing? And so that's where this connection came about, right? That wasn't in their heads at the start at all. So that then they looked at that and fed into it, and they realized they had a kind of a theoretical handle on that problem. Right, so Milgram's stuff is from the late 60s, published then. No one had really, written down a model or created a model that, reproduced what he'd done. So it was just sitting there. I mean, there were lots of speculations and so on, but it wasn't very solid. Who knows? People would explode about that, I suppose. So it turns out they're everywhere. In this paper, actually, they looked at this is a very tiny network, 290 nodes. If you look at how languages can, languages like a thesaurus, for example, small world things, and we haven't quite defined what small world is, but it's going to have short distance and clustering, right? Somehow. We'll show you how that works. Food webs, all sorts of things. I mean, there was a paper in Physical Review E about comic book characters. It was from the X-Men series, I believe. So if they appeared in the same scenes or something, and then, of course, someone either happily went back and read all of them, or just there was a database, so okay. So they're real, what's that? It does get complicated, yeah. Which sort of helps with the whole shrinking the universe thing, yeah. A lot of crossover. Oh, so there's the one for, does anyone know what this is for movies and TV shows? That they're all in the same world? Do you know this thing? I have to. There's an elaborate map of this, and it's just connections between.
Ones that invent each other?
It's like all the Pixar movies are technically in the same universe.
They're all in the same universe. The idea is they're all in the same universe. Is if there's some reference, however tangential between them, then there's this map that fills in of how they're actually all the same. Do you know this one?
Even if it's like a really bizarre reference.
It's a very a lot of bizarre references, right? I mean, what's that? I don't know. Yeah, okay. Yeah. This is an observational piece, right? It's like this. Someone mentioned something about, something else in a movie, and so a bunch of people do it all the time, like Joss Whedon films or whatever. They love referencing other ones, but when they say it kind of in a real way, then it seems that what, right? All right, I'll dig that up. That's completely insane. Okay, so there are two really weak requirements for something to be a small world, at least in this original work: local regularity and these random shortcuts. So this is local, and if you like global, these are global kind of things. If you're doing random stuff, that's really a global thing. Okay, so this is actually so nature has to put its little thing on it, even though I cut it out. Try to get rid of it. But it's very annoying. I guess I should do something. Anyway, yeah, so here's the model. Let me explain this model. And you've got it in your assignment right now, but p equals 0 to 1 is this one single tunable parameter. And then you impose two other things. There's n, which is the number of nodes, and then depends how it's defined, but we'll put, if you have m friends total, you have m over 2 that you're connected to on each side, which you could say is k or something like that. But we're going to say m over 2. So this case is an m equals 4 situation. So this node is connected to the local neighbors here, and then there's one extra link here. Right, so if it's m equals 6, then there'll be another one that'll be filling in. Okay? So a very simple idea. But there's clustering, right? There's clustering. Just this extreme limit is very ordered, right? Extremely non-random, low entropy thing, and it has some flavor of socialness. Just a toy model. This is just a toy model. Absurdly, and I think I have it again later. There are two ways to go absurdly in this. One is to then think this is actually a model of the world and try to, match up real things. But you could use it, and in fact, it's been used, I think, to synchronize supercomputing situation, like basically put everything on a ring and made one of these so-called small world models. And it showed that it had all these nice features. Okay, so that's p equals 0. P is the probability that, so you walk around here and you take every link, right, going forward if you like. You can do it this way. So there's a link, so you go to this node, it has this link going forward, this link going forward, and you pick it up with probability p, you roll your, or you flip your coin that's weighted. With probability p, you pick up the other end and randomly rewire it. Okay, so you don't pick up both ends, which is another thing you can do. You don't pick up both ends. You pick up one end and you go and rewire it. Just a little game, just a little. So this is not organic. It's not growing. It's not a natural thing. This is elucidating one aspect of natural networks. Okay, so here's one that's been messed around with a little bit. This model has just been, wow, explored to death. I guess a variant that made it a little more tractable was that you would add an extra edge. So you actually grow the number of edges. So you have this, and now you actually randomly add a few more random shortcuts. And that made it a bit better. Okay, so this has been scrambled a little bit. A lot of them have been kept, right? They haven't changed. This one's been rewired. This one got broken and moved over here. So we have kind of 3 shortcuts in this case. Right, so that will change its behavior a little bit. And then this is a total mess. This is where you rewire every one of them. It doesn't give you exactly a random network because you are only picking up one end. So each node will still have well, that's got to be true. It still has to have on average the number, but if you like the outgoing ones, sort of, then it's not directed. But the ones, the way it's done is you march around. So the ones that were pointing forward, if you had a color on these things, they'd still be attached. So they can't be broken off, but you can get isolated, and you only do each link once, right? If you come back to another link, a link you've already rewired, you don't do that again. So one little bit of jeopardy you might get is that a node could become disconnected. It's not a disaster, but that can mess things up a little bit. So that's it, right? That's it. This is 1998, got published in Nature. Huge. Well, they present this model and then they tested a number of things, like how do diseases spread on these things, and so on, right? So it just tested some dynamic stuff, some synchronization. But the main piece they wanted to show, was this, right? So that 2 pieces. So this is the average. This is taken from the paper. So this is the average shortest path length divided by what it is when p equals 0. So no rewiring. So it's normalized to 1 at the start. And then this is the clustering as a function of p, right? Which you guys are figuring out. And so the story is, to start with, there's high clustering. And this will be for some value of, number of friends that you start with, whatever it is. And it's also, but it takes a long time to get to anywhere, right? Randomly, what the average path length is. So this is a large world, but a social one at this point. And that was the idea, right? So to start with, it's a large world, social. This is a small world, but not social. And then the point is that this thing in the middle has these 2 properties of being a social small world. And so that's what's going on here. These are you can see this is pretty small. We'd have to get out the paper and look at the actual number that Duncan had in here. But yeah, so there's a 1 in 10,000 chance of rewiring, a 1 in 1,000, 1 in 100. And so 1 in 100 to 1 in 10. So you're rewiring a fair number here. There's this wide envelope. It opens up where you've got a low average path length, but high clustering. So there's all possible graphs. This is a way of searching through graph space, because they're just simple graphs. There's nothing crazy. Searching through graph space to kind of tell a story, basically. Say that there's something special about these guys. At this end, now it's collapsed, right? It's been randomly rewired enough that the socialness is gone. It's disappeared, but it's still got a very average, small average path length. So this is in principle good for search, but not realistic. It's not realistic at all, but this little flavor of realism, socialness, is gone there. And the point is, this exists.
How do the edge of chaos crazy people feel about it? It's so distinguished here. It's not like
Oh, right.
stick the
Well, that
turnover.
okay. So that, you know, we've had a number of things where it isn't an exact transition.
Yeah.
So the sock stuff versus hot, for example. There wasn't this really fine point that a system has to be driven to. There's a pretty big sweet spot. And that's something you look for, right, in models. Especially if it's, you know, very abstract and not, you know, these parameters aren't super meaningful. You're happy to find these pretty broad areas of operational goodness. Right, so it seems findable. I mean, this is on a log scale, so it's a bit tricky. If you put it on a normal scale, well, I mean, it's going to happen. But you want this decent range of parameters, or decent, you know, volume of parameter space that's sort of findable. So one other thing is, you know, one way of saying this, is it dynamically accessible? Can things be built to get to that point? So when we get to scale-free networks, that's manifestly the story about things. It's all about the building mechanism. We've seen it's rich gets richer, spoiler. Yeah. Yeah. So some things have sharp boundaries, but that's not, yeah, that's a little unsettling actually, right? Because you need some, yeah, it's a little bit, yeah. Say evolution, right? You could say, okay, it is always pushing it back to some middle ground, because if you have too much mutation, then the thing falls apart. If you have too much, you know, no mutation, then it's preserved, unless it's like a crocodile and it keeps eating you, like it's good. It's like, who cares about evolution, right? Crocodiles don't believe in evolution, right? But you can evolve some nice juicy things for them to eat. Maybe they like that. Anyway, so you can imagine there's a system where things are being pushed back towards something, but you know, it could be a broad middle ground. So there's nothing dynamic about how this is produced, right? This is just a excuse me. There's all of the graphs you could imagine for, you know, n nodes and m edges, right? There's huge bucks of them. This is a way of traveling through, like it's a thin little path through all of them. So it shows you that there's a little route you can take, right? That now you're in the world of good graphs, right? You know, it's like the Charlie in the Chocolate Factory or something, and then you can go out the other end and it's bad, right? But there are all sorts of other paths to take. That's a really big complication. Feels like 1980. Okay, that beep. It's really a good beep. Okay, so here's the problem though. In this model, it's all very good, but are these shortcuts findable? And the answer is no, unfortunately. So John Kleinberg pointed this out first in a number of conference type papers that computer scientists like to produce, and a one-page paper in Nature or Science, one of them. Let me see. So that's a bit of a big deal. Yeah, it was so navigation in a small world, Nature. And so, you know, he's got exactly the right word here, navigation, right? So we've got this smallness property, right? This is this small world property, but that's structural. And then the question is, can you reasonably put an algorithm on this thing and run around? So the answer is no. And given this criterion, you need to use, if you have a map, of course, you can run around on anything, but using a locally informed search mechanism where you know something about your neighbors, you know the target, and you can kind of, you know, choose which neighbor will be closest, would be the best, right? You can't do it quickly. So there's some technical stuff that Kleinberg did, but I think the point is for that exact model that it takes an infinite amount of time, essentially, as the thing goes to it scales really badly. Yeah, a polynomial sort of thing.
So, like, the interpretation of that is that in a small network,
We'd have to get it out, exactly. Yeah.
you can't, like, figure out the shortest connection between you and a distant network.
Yeah, so the problem is, so there's no, in these original ones, there's no information, there's absolutely no information. So you start, there's a starting node, boom, and then maybe you're given this target. You're just told, so these are labeled, right? So there's 1 through n. That's all they have on them, labels. There's no other information. So what you might know is, you you know the labels of your friends. And Kleinberg added this thing, you know where the message has been. Okay, so you can imagine, that's a reasonable thing. It's been written on the message. It's coming through, it's been through these nodes. So that stops you from sending it back the same way. And you might know something about your friends. You might know how many friends they have. You might know that. But that's it. So the thing is, there's just a lot of random, you're just guessing. It's a random walker problem.
If your selected node was red and its available network was red,
Yeah.
and then everything else was black, you can see as you move through the network, your vision is only that length of your network, right?
Yeah, right. Right. Each node has this very limited world.
You could just try like Dijkstra on it.
No. No one's allowed to do it. It's a decentralized search. Yeah, exactly, right. But I could just code it up. You don't have a map. You don't have a map. Each node, yeah, so exactly. So you could turn the light on for this node and it would be these 4 neighbors. That's all they know about in the world. So they might know that this neighbor has 4 friends. They might know that their 2 neighbors here are friends with each other. They can know that. That's sort of reasonable. Yeah, I think, yeah. But not, nothing too much beyond that, right? So it fails. I mean, I could pull it up. I'm excited about it. I think you really, yeah. So the primary merit, figure of merit for such an algorithm is expected number of steps. Okay. It has to only use local information, right? Obviously, it's very simple. Otherwise, talks about the log n story, right? The smaller, does not. So, so he has a, and I'll show you this. He has a different kind of network that he looks at. Okay, all right. Back to here. Explode. Okay, so you can't find them on these simple ones. So you need a more sophisticated model. So what are the things? Okay, I've talked about this. What do you do if you don't have a map? You need some way to measure the distance between your friends and the target, which really you see you can't do that for that small world. There's no way you can say, right? Unless the target person is one of your friends, you're like, okay, that's a, but if it's a friend of a friend, there's no way you can measure that your friends are close to them. There's no information that's correlating. Is that right? All you know is maybe how many friends they have. You don't know anything about their friends. So these are things you could have. Target's identity, friends, so how many friends your friends have. Something about their identities, of course, but not the identities of their friends, like whether they're popular or not, and where the message has been. These are sort of reasonable pieces to put into a local search algorithm, and that's what Kleinberg did. Which again, I have to say, superhero guy, really nice guy. Okay, so there it is. So he did 2 things. He upped the story a little bit. He said, well, let's look at, this is a nice set of networks. Let's look at a whole other class of networks. So we're going to have another parameter, and we're going to do it in d dimensions because we can. And he allowed the search algorithm to vary, right? So he's not just specifying. So he wants to find the best network structure coupled with the best search algorithm. And it could be there's a whole bunch of networks and a whole bunch of search algorithms that all work together, or for a particular network, you need a particular kind of search algorithm. Okay. And it's, good detailed math stuff. So here it is. I guess I could have a map, but it's a picture of it. So d-dimensional, as I said, why not? It's a cubic lattice, and typically kind of just a cube. But you can imagine this in 2 dimensions, right? So now we've got everyone's just sitting on a lattice, a bit like that first picture I showed you. But to start with, it's just a square lattice, right? And so you're friends with the 4 nearest neighbors. And there's a limit to it. It's n by n. And then there's a parameter q, which is a distance you could measure along the network or whatever you want to do, that you go to every node and you reinforce locally the network. So q is this distance, and you start adding, so it goes to here, you add all of these connections. And you do this for everyone. Right, so it's going to be really messy locally. Right? You're going to knot it up like this. So obviously Q equals 0, you don't do anything. As Q goes out, you start to strengthen that local structure. And then on top of it, so that's a local thing, and then add shortcuts. These are not a rewiring one, this is just add, so just randomly choose 2 nodes, well, with a criterion, and start to connect them like that. And this is the probability distribution that he put together to do this. So you have some distance between 2 nodes. The probability that I and j are connected is proportional to the distance of minus alpha. So there's a weight, if you like, for each one. Okay. So you take all of these guys, you count up all the ones that are just different by a distance, whatever it is, 5, 6, 7. Add them all up, multiply them all, you get the number for each distance, you multiply them by this factor, and then sample from that distribution. So, pretty easy thing. So when alpha is 0, this is just a 1. So, and every pair is equally likely to be chosen, right? So tight, far away. Okay. So that is back to the kind of the that's like the Watts model, right? The Watts-Strogatz model, which was a random rewiring, but this is actually you're adding a link, but it is random. If alpha is large, then you are right. So alpha is very large, then this thing drops away really quickly. So you're really favoring the local connections again. Right? So there are no long distance connections being made. Right? So alpha is large. So alpha in principle goes between 0 and infinity. And then when alpha equals d, you have to think about this a little bit, but basically the connections are growing logarithmically in space, right? So you have right, so this node sees away from them, they see approximately 2 pi times, what is this? I don't want to use d again. R. Is R being used twice? So this is radius. Right, radius. That's approximately how many, this is 2 dimensions, so it's growing like R, of course, proportional to R. In d dimensions, proportional to R to the d minus 1. That's how many nodes you see as you go out. And then when you have alpha equals d, the decay is balanced just so that you're adding them so that, say, for instance, this distance and then double the distance and then double the distance again, you're getting an even kind of weighting roughly as you go out. So the random one is too far. It's too far. You're not getting any local reinforcement. Alpha equals d, you're kind of getting this nice thing where you're adding links at all scales in a particular kind of way. Right, so that's the sort of, right, and then of course below d you're getting towards random ones. Above d you're moving to more local connections. And so I'm going to add his figures. So this is what he determined. This is theoretical work, right? Greedy algorithm works best. So very simple. This is, okay, one thing that I didn't say about this. Now, this is a very important thing. This is I and j. You know your location in the network. Big change, right? So you know you're at here. And if the target is here, you know that sending the message this way will eventually get to them. Right? So now you actually do have a map. The map is just encoded in your coordinates. So that's a big change, right? So we need to move away from that again. But that's the game. So, but a greedy algorithm then says, well, if you just give it to your friend who's as close to the target as possible, right? And if there are no shortcuts available to you, you just kind of just chip it along, right? You just push the football along, right? So you go scoot, scoot, and then if there's a nice big link here, then this one is going to go, oh yeah, sure. Or if it's a link to a friend of the target, they're going to push it that way as well. Right? So it's very easy. It's an easy computation for these characters. And so alpha equals d turns out to be the best network for searching. Right? Greedy algorithm in general is the thing to use. right? Makes sense. You just do the best you can at every time step. It's decentralized. Once you make once you send the message on, you're out of the game. The next person just does the best they can. So that's all reasonable. But it turns out it's this sweet spot in the middle where you have links at kind of at all scales. So it's very much like what I call social golf, right? So you kind of have links. Links is just not even, that's an awful possible pun. But the links are at all scales, which represents, putters all the way up to woods or something, right? So the problem with alpha equals 0 is like having a bag full of woods. I don't even like golf. And so every time you hit it, you just madly smash it to pieces. If you're on the green, you just smash it away, right? Because, which is not entirely what you do, because you know to just go, just like kick it a little bit. Because it's always available to you as these little kicks. So none of the shortcuts don't help you, apart from the start, right? So potentially there's a nice, there's a link that you can go and send it very close, somewhere near the target, but after that it's like all these little incremental pieces. When you've reinforced it too locally, there are no big jumps to make. You can't make any big jumps. But when alpha equals d, you have lots of jumps of all scales available to you. So potentially you can get a big jump, and then a jump maybe that's half as big, and then a jump maybe that's half as big as that, with little very poor bits of golf in between, where you just kind of Aries, we used to call them. So he gets that the search time in this case grows very slowly with system size, like log squared of n, some various other results. So that's super, right? Really slow. I want his little figure. I had it there. So, so he's got these nice analytic results. Here's his exponent alpha. And in this case, right, there's this greedy algorithm working away, right? So this is whether you have an exponent. So here there's no, right? So here the growth is logarithmic, and here the exponent is, he's got some exact results. It depends on alpha, which is that decay exponent. So when alpha is 0, you've got 2/3, and then it's a linear decay, and then there's this form here. So the time is growing as n to this power. It's growing polynomially. And he has a result for that power. So just around it, it's still growing polynomially, but slowly, right? The exponent is almost 0. Right there, there's no polynomial growth. It's just logarithmic. So nicely done. Yep, and there's his little, there's an example of it. Right, boom, there's his example. Okay, so does that make sense? Sort of, yeah? There's some nice work recently that improves upon this. So computer science is full of analysis type results, horrible things, lower bounds and bounds, and What's that? Analysis, yeah, but we don't want to talk about that. Okay, let's get back to it. Okay, the problem is, of course, that lattice, this is not how social networks look, or other kinds of networks. This is a very stylized kind of theoretical model to play with. I'm going to point out these recent pieces of work, and I have to get my citations to work. It's lazy of me. But so that was 2000. So this is 2006, 9, and 9. I mean, it takes 9 years to improve upon these things. These are physicists showing what they like to do. So there's some good, fun things, integrals and scaling kind of results. But I think they improve upon things. So Ben Abraham's actually at Clarkson and was a supervisor of Bagro. So some nice stuff here. All right, so maybe I'll put this in more detail later on, certainly in complex networks. Okay, so there's one other piece that was pretty good, and back in the day, so this is 2001. So if there are hubs in these networks, right? So if we have one of these things that we've seen a million times, these parallel size distributions, here it again is for degree, so so-called scale-free networks, then they can be searched reasonably well, right? Because what your heuristic now is to give it to your friend who has the most friends, who does the same thing, and eventually you get to a hub with 10,000 friends, and then hopefully they can guide it. It seems that you should not be able to get to ones that are, out on a tendril. It just seems still impossible, right? You can get to a hub, but how do you get out to the fringes? But if you get to a hub who's got 1,000 friends, then 10,000 friends. Yeah. Okay, but hubs, this is debatable, but hubs and social networks are somewhat limited, right? If we talk about the ones where we say one person knows the other person in some sense, then you have Oprah's in it, and everyone knows Oprah and everyone knows Obama or whoever you want, and and there is some influence there, of course, but that's we want to have real where humans actually talk to each other.
It's called like Vodia Hub.
Voti?
Yeah.
Vote?
The building, if you pretended it was a person.
That's a disaster. That's what Vote is. It's an architectural nightmare from the 1960s.
You pretended that it was a person and knew everybody who ever went in there.
I don't know. It's just, yeah.
I feel sorry.
Yeah, that's true. Yeah. It'd be kind of like it's like a depressed robot or something. Like Marvin the depressed robot. Hello, welcome to my, I see you're studying. It's, wow. You bring out Voti. Yeah, call it Vote. That gives it some hope, but I don't know what else to say. But it's not a good way to meet, I mean, stairwells maybe.
You talk to people there, you complain
It's
about
a
how
great
much
place
work.
to just be.
You tell people, you give people advice on the exams that they're about to take, because you've obviously taken that class before.
So you spread fear and,
Yeah.
yeah, good, right, okay. It is worse than I thought, yeah.
What about instead of, because it sounds like each node is one person, so of course then hubs are going to be limited, it's not.
In their ability to move messages.
Yeah.
Yeah, that's
you
true.
only have one friend that's super friends with everyone, right?
So in fact, you avoid them a little bit because you don't want,
Yeah,
they won't do it.
yeah, but you do often know communities of people that
So
are
that's
really
so
good.
that's right. And in fact, moving it to groups is a very powerful
Just
thing.
like moving it to Voti.
So we've done some.
She really likes Vote.
Well, I'm really sorry about what's happened to you.
A lot of time there.
The good news is you won't have to for the rest of your life. So
That's my figure.
only gets better.
Well, what made me
That
think
smell
about
of
it
metal.
because,
What's it?
so I'm thinking about for my project, networks in university systems.
Yeah. Yeah. Right. So exactly. So if you moved it to a group thing and you said, let's just put a poster up for that group, or we'll send a message to them, that's a very different game. And we have some results for Contagion, which get buried in a book. Completely changes everything when you start talking about groups, and it's really interesting. So you see this with some, there are some kind of approaches to solving problems or kind of making the world better, where you take a group of people instead of say an exchange of one student, for example, you might move 3 or 4 or something. So when they come back, they're more cohesive, or they have a shared experience.
Yeah.
I mean, lots of things you can think about where you think about the
So
group.
that's my question. Are people modeling that, this kind of?
This has been so hugely explored but I don't know. I mean, definitely.
Kind of a hybrid graph, some single nodes and some community.
Yeah, I mean, I've personally made exactly those things. Yeah. And I'll show you. What am I saying? I'll show you something that. Okay. All right. Let's think about it in a different way. I mean, really, what I'm going to show you actually does that. Yeah. Okay. Good. Okay. So we can do it. Well, this is right. So we're going to move back from the Kleinberg approach, which is very clever, and it brought in navigation. It said, by the way, great network, but you can't find your way around. It just makes you angry, like Boston, driving around Boston. Right? Can't get anywhere. So how do you do this? So now you're not on a lattice. There's no map. How do you get from here to here? So a couple of things. If we talk about people, and of course we talk about informational objects, identity, right? So we've got all these things that define people in a very functional kind of way, functional identity. So where people live, what they do, their beliefs, what they, their recreational stuff. And then of course our groups are it's funny, the way I was thinking was wrong when I was... So, and then you get groups of people, right, that are formed out of these things. And we're going to do it in a simple way. If they share an attribute, then they're kind of part of a group. So if they live in the same place, that doesn't mean they're friends, but that, that's a binding piece. Of course, the more attributes they share, the better chance. So you have attributes, that puts you into context, which again give you attributes. That gives rise to interactions between people, and then in a sense you lift the networks out of that, right? And it goes back and forth, right? So you meet new people and they might have another context, right? Yeah, like they're really into Amway, whatever it is, or something. They say, come rock climbing, whatever it is, right? Okay. Okay, so here's the starting point for this. Yeah, I can throw this up. Bipartite affiliation networks. So they might have context, right? This might be their workplaces where people work, or their major, or whatever it is. If they're student types, so here are the individuals, and they share these contexts in some way. So A and B know each other because they share this. This has to be something where people have more than one attribute. So, it could be movies and actors. It could be, boards and directors. These are natural kinds of things. Could be the sports you play, whatever it is. Okay. But there's some sense that these contexts are similar. So from that, you manifest a network. And it's so we talk about bipartite affiliation graphs and then a unipartite network. If E starts to act in this context 3, then they have a chance. They already know C, but they have a chance now of meeting D and B. And so that's what's happened here. Right? These connections have been added for E. Fair enough? Kind of thing. So what people tend to do is spend too much time thinking about this, but this is really the way a lot of, this is the way to think about a lot of networks, especially social ones. Okay, so we can say something about these contexts. So for instance, this is where we want to think about the identity. So here's an example of occupation. So again, we've got our 5 characters, and maybe they have these roles. So these 2 are high school teachers. There's a kindergarten teacher, so they're in education. They're somewhat similar to each other. These ones are more similar. And then you'd have another hierarchy underneath this. Might have someone who's a nurse, someone who's a doctor. They're in healthcare. They have occupations, right? So there's some way we could talk about their relatedness, and it depends how you can pass these different things, right? So occupation may be nicely broken out in a taxonomy that looks like a hierarchy. Actually, geography is weird because of travel, right? It's not what it used to be. So, and of course, there's the actual shape of the land and where you can put cities and so on. But how people know each other through geography is complicated. So, a simple thing to do then is to just explore these kind of hierarchical models. So we've got a few nodes in here. There's I, K, J, and V, or new. And in this case, we're going to have groups. So we're going to stick to the group story. We're not going to have this go all the way down. This is an important piece. In here, there are groups of size 6. There's a branching ratio of 2. And so we'd say the distance between I and J is 3, right? So this is the height of the lowest common ancestor. So anything that's in the same group has already got a distance of height 1. So you can imagine there's like a bunch of little things coming down here. So there's a 1, 2, 3. That's the lowest common ancestor in this graph. So that's a sense of their distance, right? I and V is 4 because it's over here, and then you'd have to come back to here. Fair enough? Okay. So very much like Kleinberg, you have some decay of how people, how likely people are to know each other. We're going to create the network from this structure. It's going to decay as an exponential, which is kind of okay because of this exponential structure of the hierarchy. And we're going to give them Z friends each. There's going to be some, we'll have to normalize this, but we have the distance again based on the lowest common ancestor in the hierarchy. So random connections for alpha equals 0, similar thing. Alpha equals large, local, we're just reinforcing or making local connections. Right? There's no underlying network, we're just going to build it on top. We'll give everyone, a reasonable number of friends, and there are studies on how many friends people have, and back in the day it was like 300 was sort of a measure for Americans for the US population. Of all types, of course. I mean, you might have a few that are very tight friends, and then you have a hierarchy, if you like. So one way to then proceed is to say, well, all right, you have these you have different attributes. So there's where you live, there's your occupation, and there's your age. And this might not be a hierarchy, right? This might be better thought of like this, but it might be clumped as teenage versus, then, you might have different ways of breaking that structure down. But, in principle, that's probably a sort of a linear kind of thing. The way we did it with a model was just to use hierarchies because we had to do something reasonable. And this ties into all of this great literature in sociology, going back 100 years, talking about circles, which is the Google circles kind of story, which hasn't really taken off. But they're trying to reflect something that's really true about, social, right? You have this group over here of friends that you go kayaking with, and maybe, and that's sort of a circle you go in, and there's another circle over here. Maybe it elicits different behaviors in you. It's all good stuff. So then we did this, right? So we added 3 more. Okay. If I run out of time, I've run out of time. Okay, I'm going to finish this on Thursday. I'll take you through the rest of this model, but I think we've got the basic idea, right? It's going to be about identity, and I'll show you that it does a pretty good job. All right, so, okay, more on small worlds, and then we'll have the scale-free network. Talk faster. Okay, monologuing. All right, if you want to work on Twitter, you should, yeah. I'll send you an email about this. Okay, people, thank you.
Yeah, you should email me.
If you like